In our first lab, we analyzed the relationship between position and time, creating a position versus time graph, a very important graph in the world of physics. Understanding the relationship and the different elements of this graph helps you really understand constant velocity. To reiterate the two terms that we learned for our pre-lab, we've talked about velocity, which is how much distance an object travels in a given amount of time. The velocity not only tells the amount of distance or displacement that an object has traveled, but the direction, forwards, backwards, etc. A constant velocity is one velocity that does not change. It stays the same. There's no speeding up, no slowing down. This is like cruise control on a car. Whenever we talk about constant velocity, we do not use the following words: speed up, accelerate, or slow down. An object that's moving at a constant velocity does just that. It stays the same velocity throughout the entire motion. It does not speed up, it does not slow down, it does not accelerate. It starts and stops at the same exact velocity. We first saw the position versus time graph during our lab. When we did so, we had plotted the position in meters on the y-axis. This was our dependent variable. It was the variable that we measured. Time was plotted on the x-axis. It's the independent variable, and it's measured in seconds. Time is the variable, second is the unit. The slope, which is the relationship we observed during our lab, is velocity. We know that because if we take the slope, which would be rise over run, or meters over seconds, or meters per second, that's the unit for velocity. Understanding how a slope moves through a position versus time graph tells us a lot about the object's motion. So let's understand these trends. The steeper the slope, the more distance is covered by an object. So therefore, the faster the object's moving. The opposite is true. The shallower the slope, the less distance is covered in a set time, and therefore the slower the object. So car A may have driven 2 miles in the same amount of time that car B drove 1. Car B is therefore driving slower. The shallowest that a slope can go is 0. A 0 slope means that no distance is traveled in a set time. At any given moment in that line, the position is always the same. When you're not changing position, you have a 0 velocity. The object is not moving. Time keeps moving forward, but the position remains the same. The steepness of a line tells us its speed. It tells us just the magnitude of how fast it's going. When we're dealing with velocity, though, we have to have a direction as well as a speed or magnitude. The direction of an object is signified by the sign of the slope. If it's a positive slope, like car A, that means that it is rising on the right, position is increasing as time increases. We would call this moving forward. This is an object that's moving away from the starting point. So if we're looking at a starting point here of 0, if these two cars were on a racetrack, for example, car A is moving away from that initial starting point. If there's a negative slope, like car B, that falls on the right, it's moving backwards. That car is starting further down the racetrack and moving towards the initial starting line. It's moving towards 0 as time goes forward. We describe motion similar to how we observe motion on a graph. When we describe motion, we can talk about it in 3 easy ways. We can talk about the direction of the motion. Is it moving forward? Is it moving backwards? Is it stopped? On a position versus time graph, a positive slope means we're moving forward. A negative slope means we're moving backwards. A 0 slope, so just a straight horizontal line, means we are stopped. There is no change in position over time. The type of motion we look at, there are 3 main types: constant velocity, stop, which is a version of constant velocity, where your constant velocity is 0, and then acceleration, which we will get to. We can also describe the relative motion between 2 different objects. For example, you could talk about how one object's faster or slower than another object by looking at how steep or shallow the slope is. You could also look at the direction 2 objects are going. They could be going the same direction, the opposite direction, depending on the sign of their slope. Let's apply our knowledge to a position versus time graph with 3 cars. car A is moving backwards. We know this because car A has a negative slope. The position is going down. It's going back towards the zero or the origin point on that graph. As time goes forward, position goes down. So it's moving backwards. It's constant velocity because a straight line on a position versus time graph means constant velocity. It means position is changing at the same rate that time is changing. A straight line always means constant velocity in a position versus time graph. We also know that car A is moving faster than cars B and C because it's a steeper slope. Car B is stopped. It's a horizontal line. We know two things here. We know that a horizontal line is a zero slope, so it's 0 meters for every second. We also know that a positive slope is forward, a negative slope is backwards, so a zero slope is neither forwards nor backwards. You're standing still. On your own, try car C. Describe its direction, the type of motion, and describe whether it's faster or slower than cars B and C. Cars B and A. Although the slopes of graphs can tell us a lot in a position versus time graph, the interactions amongst those lines can tell us a lot as well. On your own, do a little think, pair, share. Think about what you think those different intersections mean. If you were watching cars A, B, and C drive, what would happen at those three intersections?